Hello everybody, welcome to my video on ADC on STM32. So this is a follow-up on our previous videos where I discussed how to use USART, or in our case UART. So this code that you see here is the same code as from before, with while loop empty, but with GPIO set for all the LEDs on board and the USART as well. So USART is also set up. For convenience sake, for future projects, I also put all the clocks in a separate function, so it can be managed easily, because I had some problems and I found a way that if everything is in its own function, it all looks better for developing. We want to use an ADC on our board, so I'm just gonna go to the picture of my development board. I decided to use a ADC pin. So here are all the pins that are ADC capable. So if I look at my board, I have a potentiometer and it's connected with this link to a pin over here, and I chose A0 because why not, the first pin that is available. So the first data we need is which pin we want to use. So you choose your pin and then let's go to the datasheet. So I have datasheet for my STM32F407, which is on the board. And we want to go to the pinout and pin descriptions, which is this one. I want to scroll down and search for PA0. Here it is. Let's zoom in on that. So our pin PA0 has all this function available and ADC. What does this mean? This pin can be connected to one of those three ADCs. So this microcontroller has three separate ADC peripherals inside. So this tells that this pin can be connected to ADC 1, 2 or 3, and it's on input 0 on each on one of those. So ADC 1, 2 and 3 pin PA0 is connected to input 0 or channel 0. Note that not every pin can be connected to an ADC. Here you can see just a dash, and not every pin can be connected to any ADC. So if we go to the next line here, we can see that PA6 can only be connected to pins ADC 1 or 2. Also, the input number doesn't correspond to the pin number as well. The PB0 can be connected only to ADCs 1 and 2 on input 8, not on 0. So please make sure that you read this number correctly for your particular pin on your microcontroller. Next, we can observe the data that can be read from our ADC. Our ADC, which says in the datasheet, is 12-bit. So we go to the reference manual, which is this huge manual that holds all the data about this microcontroller. And we scroll down to ADC. Here it is. I want to see all the registers. So if you haven't seen the register map yet, here is how it goes. It's a 32-bit register, each one of these, and it holds all the important data. All the GPI initialization, USART, and in this case ADC initialization is in this file here. And the last one is the one we care about. It's the ADC data register. We can see the first 16 bits are reserved and the 16 bits are the data. But we will just use the first 12, that's the data bits. So now that we know this, we can go back to the code. Let's start. The first thing is initialize the clock. This is the first rule. If we go to the adc.c, the first one is initialize the clock for ADC. So you go to the rcc.c file and search for ADC1. And we will find that APB2 bus can be connected to ADC1. Great, because we already have APB2 for USART1, which is over here. So let's just copy this one and add it here. Great, our ADC is enabled. Next, we need to enable our clock. I chose pin A0, so you need to enable clock for the GPIO A. I just add it here and just change it to A. Great. Now we need to configure the pin. The pin has to be for analog read, so we can go to gpio.c file, scroll down, and here we can see the GPIO options that we discussed before, and we're interested in mode. So we go to gpio.h and search for mode, and now we want the AN. This is the mode for the analog. So we can just copy a few lines. So we're gonna need initialization, the mode, and the pin. We want only to initialize pin 0 as AN. I'm just gonna remove this and initialize it on GPIO A. Great. This is the GPIO portion. Now we need, as with USART, now we need to initialize the peripheral. For that, let's just create a new function. I'm gonna call it ADC1 setup. And let's copy it. And we're gonna call it in the beginning. Here. Let's make it neat. And let's define it right behind USART and before our user functions. So we have taken care of the clock. Now we need to do the initialization of a structure we can anticipate. And you're right, but we have two structures. If you scroll down, we have an init struct and a common init struct. A common init struct has only 4 parameters, but they are global for all ADCs. So it initializes the ADC peripheral according to specified parameters. So we can use this definition right over here and remove the asterisk and the init structure. Great. For a template, let's just use all the default values that are here. We're gonna use the default values, but we can copy them here so we can later see what we were doing. So if you want to change it later, you can. Firstly, we're going to use the independent mode. If you don't know what it is, let's go into H file and here are all the modes. So here's the ADC mode. We want the independent. You have all the other modes, but we're going to use only this one, so we're going to use independent. Next is Prescaler. This is the ADC Prescaler. We want the fastest, so division 2. DMA access mode will be disabled and the sampling delay will be the smallest, which is right here. So it's gonna be the fastest. So we can just leave all this like this, and I'm just copying here because if you want to do anything different later, you have all the options already here. Plus, don't forget to zeros. If you forgot, you can hold Alt and Shift and arrows up and down to select multiple columns, but you have to click Escape to reset it. So to initialize our settings, go back, scroll up, ADC common init, and as you can see, with any init, we have to specify which peripheral, but because this is the global one for all ADCs, we just need the structure as an input parameter. Next, the specific ones for the struct init are these ones. Only difference is the two are global. The resolution and data alignment are global. So I like to copy them together at the beginning, so know they are global. The resolution, we're gonna keep the maximum 12 bits, but you can go back to the H file. And as you can see, we have 10, 8, and 6 bits. So if you want maybe faster, or you don't need that resolution, you can do that. Also, we're gonna have a write data alignment, which is the default value as well. So these are the global. This one now relates to the specific ADC. The scan conversion mode dictates whether the ADC is gonna switch between multiple inputs. But because we are using only one pin, we can leave this disabled. But if we were to use multiple input pins, maybe we will do this in the next video, we will enable this one. Next is the continuous conversion mode. We're gonna enable this one because this mode does is tell the ADC after each conversion do another. So it's gonna keep converting values over and over and over and running in the background. And we're just gonna start and pick data randomly when we want to or on a regular basis. But this is so the ADC keeps converting the latest data, so you don't need to tell it each time separately. But if you're on a battery project or something, you don't always want to have this enabled because peripheral running all the time in the background, it takes energy, but we don't care about that now. Next to are also default because we won't be using any external trigger for making the conversion. And also we're only gonna do one conversion because it's only one pin and one conversion at a time. Again, change this to 0. We're dealing with the instruction, not a pointer. And now we need to initialize it. So we're gonna scroll up to ADC init. As we can see, here we have to specify which ADC peripheral. We chose ADC1 and ADC init struct. Now we need to tell the ADC from which pins for it can take the data. So we're gonna scroll down, way down, and in the beginning we read that we can have two modes, the regular or multi-channel. Here it is, the regular channel configuration. Regular channels is when you have only channels for this ADC, but multiple channels can be for if you're using multiple ADCs at once, like ADC 1, 2, or 3 at the same time. Here we're going to use this function, regular channel config. This is going to configure the channel appropriated to the ADC. We're going to configure channel for the ADC1. Which channel? Well, we saw that in datasheet, where it is? Here it is. Pin A0, which is here, is connected to input 0. So the channel is channel 0. We're just going to copy this one. Next is rank. It's quite straightforward. It's the regular group sequencer. You have multiple channels. Let's say for reading, let's say it's channel 0, 1, and 2. So 3 channels, and you want to sample them in a certain order. First channel 0, then channel 1, then channel 2, or any order you wish. So you put in a rank from 0 to 16 as it says here. We have only one channel, so I'm gonna put in 1. But if you want to read multiple channels and you know in which order you can read data, you can copy this function multiple times and give them different ranks, let's say 1, 2, and 3. So you know you're reading firstly this channel, then this one and this one. So when you're reading channel data from ADC register, you know which data it is at the time you're reading it. So this is important if you have multiple inputs. Then is the sample time, which is the time that the ADC gonna sample the certain channel. And we're gonna use a rather slow one because we want the data to be sampled a longer time, but we don't need fast acquisition. So you would want to decrease this number so it can be done faster. This is for stability purposes and we don't need to rush, so you can choose any one you want. Now that the channel is configured, we need to enable the ADC or start the ADC peripheral as with usart over here, and it shows that it's the same command. So I'm gonna do ADC command, and we can also go here to search for it. Here it is, and the peripheral and the first argument is which one? ADC1 enable. Now the ADC is configured and starting, but it hasn't started doing conversions yet because that takes battery. So you would want to start to tell it to start making conversions. So we scroll down. So let's see where that is. This is the regular channel config, after start conversion, and this is the one we want. So this function tells the ADC to start converting. So let's copy this function. And we're gonna put an argument of ADC1. Also, if we go down, we can get the function get conversion value. So this is the function we're gonna use to get conversion value, and you can see it's a pretty basic function. It just checks if the input is right, as with every function, and then it's gonna write to the appropriate ADC data register and request the number. So it's gonna read from this ADC data register. So we could just use this simple line of code, but for development purposes, you always want to use functions because it's easier to debug and share the code. So after this setup, our ADC is sampling all the time. So now let's take the number. We go to our while loop and let's create firstly a global function if you need it, but let's say, and we can see that it's a 16-bit number at most. So we're gonna create a 16-bit ADC data variable, and let's put in the number by using this function from ADC1. If you remember from USART, we can just read all as fast as the processor can because the ADC can be slower or mid data, so we're not necessarily taking the latest data, or we can just send the same data multiple times, and that's just nobody needs that. So we need to wait until the latest data has been converted. With ADC we also have flags, so let's search for flags. Oh, here it is, interrupts and flag management. We go down and here's the function ADC get flag status. We want to wait in a while loop or in any loop until the flag for the conversion is 1. So let's put a while loop with a not. So until this function is 0, this while argument is going to be 1. So we're going to stuck in this while loop. So the argument first is which ADC, ADC1, and then which flag. We want this flag. This is the end of conversion flag. So this flag is going to be 1 when end of conversion is reached. So until that, this flag status is going to return 0. With not, it's going to be 1, so the while loop is going to keep the processor busy. So this is why this function or this method is very inefficient, because the processor is just going to waste time until the flag is completed and not do anything else, which can be important if you have multiple things to do. Let's send this number by UART by using one of our previous examples, ADC data function, and let's just add a new line. So measurements are going to be one after another vertically. So let's just send a new line command, and that's it. Don't forget to add a source for the compiler to compile the ADC as well, and put in your username. And let's open our terminal, run make. Everything looks okay. Let's burn the data. Okay, let's go to our terminal. Oh, here it goes. Let's go as fast as possible. Let me turn on the camera. So here's the potentiometer, and if we change it, here's the farthest. It's on almost 0, and then it's going up to 4095. 4095 or 2 to the power of 12 is 4096 minus the 0 character, so 4095, which is the maximum of 12-bit ADC. Great. Another thing, well, this video is quite long, but let's just add this. Let's convert the data to a float. So we're just gonna have ADC data as a float now. No problem, because float is 32 bits, so it's gonna get the conversion value, no problem. So let's just convert it to float just for the sake of it. And then we're gonna convert this float because it has a decimal number or decimal place. We need to convert it to a string. To do that, there's a function in C called printf. Yes, printf. This function takes a number and puts it in a buffer, which is a character array or a string. So let's create that. Let's make a character array buffer and make it size 10. It's gonna be enough for all the digits. First parameter is where to put numbers. Next parameter is the type of input. In our case, it's %f for float and ADC data. So we're gonna put ADC data inside buffer, and then we want to send text this buffer. Remember, the buffer is the name of the variable, and it's also a pointer to the beginning of this character array. So this is gonna be like a text. So it's gonna send buffer and then a new line. Also, we need to include a library. It's a standard library called stdio.h. So let's go back to our terminal and just reset our CPU. Oh, and as we can see, it's a decimal number. Now we need to convert it into volts. So to do that, we need to multiply it by the resolution of the ADC. Resolution of the ADC is the reference voltage of the ADC divided by the ADC resolution, which is in 12-bit in this case. So how many volts per bit can this ADC detect? So if we multiply the ADC data, which is in bits, you can say, the bits can cross each other and we're left with volts. So we multiply with 3.3 volt and divide with to the power of 12, which we can write as 1 left shifted by 12 places. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if we have a 1 here, we want to shift it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The 12th place. And this is the 2 to the 12th power. If the first is 2 to the 0. So just if you didn't know that, we can save that. Assign it to our microcontroller. Ctrl Shift M. Let's reset it. And you can see it's a 0 volts. And if I turn it, it stops at 3.3 volt, which is correct. Great. So it's working. So this is the basic code for any project that you don't need much CPU power. So this should be good enough for everyone. But if you want to have it automated, we're gonna do the next video using the DMA or Direct Memory Access, which is a peripheral inside your microcontroller. Well, actually, it's in most microcontrollers that can copy the data between data register and the system memory. So it can copy the data from our data register, which is this function right here, into our place where the variable is, so the CPU doesn't have to. So we will only use the CPU to take this data and send it over to UART. But that's for the next video, so thank you for watching and see you next time.